let's get started. So, welcome back, and it is good to see all of you and to interact. Today, based on our schedule, is supposed to be our Friday fun day. We've fallen sort of half a day behind, so one's definition of fun may be a little bit malleable depending on what mood you are in. I'd like us to continue on that lecture 2 topic, if for no other reason that there's another homework coming out, and it does kind of expect you to have a decent grasp of these concepts. I never really know for certain until this second homework comes around if if you're finding that this topic is going too fast or too slow. So really, I'll cover it at a pace that seems reasonable given the very low level of interaction we have together. And then we'll just see based on offline chat on this lovely August 28th here today, 2020, that if you're still having questions about that. Where it does start to become fun, I think, is that the connection between the assembly we're writing and the underlying microarchitecture is going to become more and more clear. On Wednesday, we already talked a little bit about that, right? We drew some semblance of a register file, and then that will be your lab number 3. As we move to this next topic here, the sort of subtopic within lecture number 2, you'll see the microarchitectural implications as well. They're a little trickier. They're not something I think you would have seen in a 281 or 288. It's definitely new stuff for this class. But this is where we left off on Wednesday with just the example of loading from an array in memory and using a variable as our index into the array. We see that the ISA for MIPS itself allows for us to encode constants as part of an offset into an array. That allows us to do things like, in this example here, POW2 of a plus 7. We don't actually have to do the math of a plus 7. We can directly encode that 7 in the instruction itself. But for the A, and for those constants as well, the big takeaway from Wednesday, and then I did upload a short secondary video that went through a more in-depth example after Wednesday, is that as MIPS ISA is assuming this byte addressable array in memory, but we are operating on these multi-byte entities here, be they 4-byte integers, 2-byte shorts, something that's even larger than that. We have to do a little bit of that pointer arithmetic ourselves, and by ourselves I mean as the compiler or as the person that's going from C code down to assembly and translating that code. And it tends to take the form of a multiplication by a power of 2. And that's why you see in these code examples uh, forever, really, in this MIPS, is shift left logical by that equivalent number of bits to get the equivalent of the multiplication by that power of 2. This design pattern you'll just see over and over again in your translation from C code that's dealing with arrays down to the assembly. Sometimes if it's a constant, that I think that was the example on the previous slide we left off on, the constant itself, we do that multiplication offline, I guess, because we know it's a constant amount. We don't need to do it at runtime. So that's why we go from 7 here to 28 in the load word example that we have here. But then if it's an integer, or excuse me, if it's a variable that we only know at runtime, we actually do have to go through the process of calculating that offset in terms of bytes. So for integers, we'll be seeing that times 4 type of operation, quite a bit, followed by adding that offset in number of bytes to our base address, which is just our assumption that it's stored in that register S3, and then finally followed by that load instruction that's required to actually grab the value. So it is kind of that 3-step process. Calculate offset in bytes if need be, add to base address, which is just some register value stored somewhere, and then take that together and do the load based on that calculated pointer arithmetic that we have done there. And then finally, you'll just see that that's for the load class of instructions. For the opposite or the corollary instruction where we're writing things back into memory, that's referred to as store, and it's just the reverse. And so the instruction looks extremely similar. We just have to keep that mental model straight in our mind that which way is which. Load is relative to the processor. Store is also relative to memory, that we're loading something from memory into the processor. We're storing something from the processor into memory here. Otherwise, the actual instruction itself has the same exact semantics associated with it. We are taking a value we want to actually write in memory, So that's not going to get updated. That's going to be a value we read from our register file. And then we're doing the same exact pointer arithmetic for our store as what we would be doing for our load word. They're identical, just the direction of data transfer is all that is changing between them. I won't belabor this point too much. There is that nice video you can find on Canvas under the week 2 link for Canvas that goes into a somewhat more convoluted example. Um, but depending on your data type size, and here we're just focusing primarily on the sort of core built-in language data types in C. Uh, the amount we have to do for our shift will change. So if there's a short array versus an int array, and in this class, if we say something is a short int, that's 2 bytes. That's just our assumption we're working with. It doesn't have to be the case, so that's the case in this class. So our actual array is much more compacted in memory in terms of that offset becoming 2 between each element in the array versus 4. And the only thing that ultimately really changes in terms of our instruction sequence here is we would do a multiplication by 2 versus a multiplication by 4. And then it is technically a different instruction when we want to just load those 2 bytes versus loading those 4 bytes. And that instruction is referred to as load or store half versus load or store word. I think I mentioned that that term word is very ambiguous, but in MIPS, that's referring to, and in 32-bit MIPS, that's referring to that 32-bit entity. We're grabbing a word of data, that's 4 bytes. Half word is then half of that. At least store byte and load byte is unambiguous. That's just our single byte of value that we're grabbing. There's a little bit of additional complexity when we think about how one actually goes about implementing those stores and those loads. For the word instructions, there's less ambiguity. We calculate an address, we either read or write from memory. For the half words, it's not as clear. Storing, it really depends on what bits inside that register we're actually interested in. And the ISA does tell us what we need to do for that. That yes, we're treating this as our source register, register 1 here. But because we're only storing 16 bits into memory, we're actually only going to store the lower 16 bits. For the loading of half words, there's also a similar amount of ambiguity here that we have to quickly cover. That we're loading a half word, but again, register 1 is a 32-bit value, so we actually do load those 16 bits from memory, but we're overwriting the entirety of register 1. And how we do that depends on what variant of the load half word we have here. There's load half word, which is going to sign extend the 16 bits to make it a 32-bit value. And then there's load half word unsigned, which will zero extend that 16 bits to make that 32-bit value. We talked about on Monday how the word unsigned is kind of overloaded in MIPS. We already saw the add unsigned instruction, where I said that that's probably not the world's best term, because unsigned in that context really means add and ignore overflow. In this case, at least, where we're using the term in a completely different context, at least it's consistent with how you would see it used in C itself, where we could define an unsigned short int versus just a short int. And the implication is that it's an unsigned integer, it's representing a positive value. So when we want to load that positive value into a 32-bit register, zero extending that quantity makes a lot of sense. Sign extending wouldn't. It would turn it from a potentially a positive value to a negative value. And same for the load byte versus the load byte unsigned. So here, this no longer has anything to do with overflow. It has to do with how we're interpreting that 8 or 16-bit quantity that we are getting back. So it's not really, quote unquote, I would say, wasting the register value. That's a really good question. We are overriding the entirety of the register, and in our 2's complement representation of integers that we may want to be storing in our register file, we're getting the equivalent integer stored into the register. It could be thought of as a waste. You can imagine scenarios in which you're packing multiple integers into a single word, and we will cover that a little bit. But in terms of storing the correct value, it's doing what it's supposed to be doing. If we want to store the value of 3 as our integer into a register, we don't normally think of the registers being wasted in that context. It's 32 bits, most of them are zeros, and that's okay. That's just our encoding for that 32-bit value. And same for when we do these load bytes or load half words. we're loading a 16 or an 8-bit value. We just are using this 32-bit storage element in the register file to represent the equivalent integer we would have there. That's a good question. Um, I guess that's also, it depends on what you think of as waste. I guess it could be thought of that way. It allows us to pack things together in memory if we want to as well. So it may be more efficient in memory and then less efficient in our register file. There is an alignment restriction that we tend not to run into too much in the assembly that we write in this class. This is part of the ISA that it does require that data is required to fall in addresses that are multiples of the data size. So if it's 4-byte entities that we're loading and storing, the addresses we're supposed to be generating have to fall on those 4-byte boundaries. So you can't do a load word from address 2. That would correspond to this not aligned example that we would have here. We don't see that often. The simulator we use will let us know if we've done that. It'll just throw up an error. When we're implementing it ourselves in the lab, um, we have to be aware, very conscious of addresses and they're being generated. We tend to see that happening, and our failure mode tends to be a little bit different. We'll just load the wrong bytes from memory if we do that incorrectly in our lab implementation. That does have some implications if we then have more complex data structures that are composed of single bytes, 2 bytes, and so on. We do have to be careful that because there is that alignment requirement, we actually have to do some padding in the structures themselves. It really depends on the ISA and to some extent the underlying microarchitecture for a given ISA, whether or not memory alignment tends to be required, whether it's just recommended. In MIPS, that alignment is required. It's considered, a performance benefit by requiring alignment. You're putting more pressure on the programmer to reorder their elements inside a struct to pack things into memory. But then your architecture for doing the loads and stores winds up being simpler. I don't want to belabor the point too much. It's not a terribly important point from our implementation perspective in this class, and there's other stuff I'd like us to get to today. And then finally, this should look a little bit closer to like a CPRE 288 type figure, um, where we have our CPU and our memory figure, but then we also have our I/O space, our so-called memory mapped I/O, which is a very common way of supporting I/O in embedded systems, um, as well as in general purpose systems, where from the perspective of this class, where we're worrying about the details of our MIPS processor and all of our implementation happening here, there's really no architectural implications of doing memory mapped I/O. There has to be some decoder somewhere here that determines that a certain address range corresponds to I/O versus corresponds to memory. But in terms of the ISA, in terms of the loads and the stores, we can use those same exact instructions. They don't change at all, right? We're loading and storing, and we just have to be aware that this particular address corresponds to some I/O register that we want to read or write to, versus these other addresses correspond to just our main memory that we're wanting to read or write from. And otherwise, it's exactly the same. We use the same exact instructions. MIPS, for this reason, doesn't require any specific data transfer instructions for I/O. We just use the same exact class of instructions there. There's a question about that. So how is each element in an array offset by the size of the data type if the register is 32 bits? Um, anyway, let me make sure I'm interpreting that question correctly. Each element in an array offset by the size of the data type if the register is 32 bits anyway. And I don't think I drew a decent picture of that the other day, and I don't have it on me. We don't think when we think of that alignment requirement, um, the memory itself is going to be presumably just packed with that data in this example that we have here. So, right, this is not what our memory physically looks like. This is a logical model of our memory, right? Physically, a memory is just this, rows and columns of individual bit stores, and then a lot of decode logic to determine what address corresponds to which bits that we want back out. So our memory is presumably going to be aligned logically depending on the data type. If I have an array of shorts versus an array of ints versus an array of bytes, the assumption is that it's just going to proceed sequentially in memory. And then it's when we load it into the register, all of these shorts, if there's 8 shorts here, if instead we loaded them into 8 registers, you would see something that kind of looks like padding for the reason we previously mentioned. It's not really padding again, it's the equivalent values just stored as 32 bits. But in terms of the total number of bytes of storage, once we've loaded all of these into the register file, that's very correct. That if this is 16 bytes of memory here to store our 8 2-byte quantities, when we then load that into the register file, it would actually require 32 bytes in our register file because we can't just load 16 bits into a register. We would be loading the entirety of that 32-bit register and zero padding or sign extending the value to get the equivalent integer back out. So it is, in some sense, it is kind of, we do kind of have to pad things that's stored in our register file. In practice, it's not a primary consideration. We need to get things into our register file to be able to do the arithmetic on it. For the vanilla baseline 32-bit MIPS, there's no advantage to packing things together inside the register file itself. We will briefly talk about some extensions that allow us to take advantage of packing things in the register file. Not for a few weeks here, though. So that's really all I have to say about memory instructions in MIPS. I do think that that video that I posted separately on Wednesday is a good one to look at. You can play it at 2x speed just to get a feel for, okay, I claim there's this design pattern of sort of three instructions of shift, add, load, and that's all that example is going through. Just a somewhat more advanced example than what the textbook provides of shift, add, load, and how that corresponds to our array addressing. If you remember um, the 4-byte entities that we're loading and storing, and then that MIPS is considering everything a byte addressable memory, and that's why we're doing the times 4 to calculate the equivalent addresses. You're in pretty good shape, and that's what you have to kind of remember, that I'm doing loads. Do I need to do some shift left logicals here? And then that's really all you need to remember. That's the trick, and that's what that video on Wednesday goes into some depth and talks about. So this is a little bit of a context switch for us here. So I apologize for that. I guess it would have been preferable if we got this all previous stuff done on Wednesday. So a bit of a context switch. Still talking about MIPS, but now a completely different class of instructions. These are our instructions for changing control flow, right? So far for the instructions that we have covered, our adds, our subtracts, as well as our loads and stores and the variants of those really don't allow us to change control flow at all. And you can think of if the word branching makes more sense, that they don't allow us to branch at all. So what we would really have only implemented if we implemented a processor that supports only those categories of instructions would basically be a calculator and not a computer, right? The ability to make decisions based on data is what classifies something as a computer versus just something that does a sequence of calculations. So we always do need some way of changing control flow. And again, that's a term that maybe you don't hear a lot, but it just refers to control flow as determining which set of instructions or which instruction is going to be next after we've completed executing the current instruction. That is the flow of control through a program, or how we control the flow of instructions as they're executing through a program. So that's all it's meant by that term. If you just want to use the term branching and how we support branching, that's also fine. They're referring to the same things. I won't draw it right now, but we can always visualize our execution as being a graph of from instructions to instructions. And so far, that would have been just a straight line graph of add, then sub, then load, then shift left logical, then add, then load. It's a graph still, but it's just a straight line graph. But modern software, anything that requires making any decisions, is going to have branches in that graph. Think of your if else statements in C. Um, if this value is something, we go here. Otherwise, we go here. That is a branch in our control flow where there's two arrows in our graph, two edges in our graph, depending on something that's only calculated at runtime. That's what's meant by control flow. And every ISA, every CPU requires some mechanism for efficiently determining what the next instruction should be to allow it to branch. And we know all those common C examples of changing control flow. If else, for loops, while loops, case statements are a way of changing control flow. Any others that we can think of? Other ways of changing control flow in C? So one of my favorites, and for some reason people are told, for their entire life that this is evil and not to use. I don't know if this is going to work. Hold on. Is the go-to statement, and that's perfectly valid C code. The go-to statement. Let's see here. Go-to is perfectly valid. Where in your C code you have the go-to and you say go-to L1, and then somewhere else in your code you have an actual label in your C code. It's kind of looking a little bit like our VHDL labels that we're working with, right? Where you say, so case switch, if someone's going to say go-to, thank you. Function calls are also control flow, and we'll talk about function calls as a separate first order, citizen of MIPS here, a fairly annoying one that we will get to. But go-to is perfectly valid C, and I know introductory programmers, are told by their instructors, "Oh, go-to is harmful. Your code is going to be terrible if you use go-to statements." That's definitely not the case. I mean, it really depends on what your goal is with the code, and there are all sorts of advanced and meaningful and production code bases that use go-tos throughout. And oftentimes, when we use other higher level languages that don't even have that as a feature, in their actual underlying implementation, they're sprinkled throughout with go-tos to change control flow to very specific statements. That's literally saying, don't worry about uh, anything about data, just literally have the next statement in our C code that we execute be the one that's associated with that label. That would be referred to as an unconditional change in the control flow. And MIPS and most ISAs have a very common terminology that refers to changing control flow. Conditional changes of control flow are referred to or is known as branch instructions. Conditional meaning based on some condition. That's all that means. That's referred to as branch instructions. Whereas unconditional changes in control flow, in MIPS, those are referred to as jumps. So MIPS does have different branch and jump instructions, one of which says, maybe I'll change my control flow. The other one says, no matter what, I will change my control flow. That is not the case in all ISAs. A lot of them just have branch instructions for which there's a certain special case of branch that's effectively could have been called jump. It just doesn't have a different opcode associated with it. And then the terminology we use when referring to our conditional and unconditional branches in MIPS is very similar to our go-to terminology, where we're going to branch or we're going to jump, and there's going to be a target, what we want the next instruction to be, and that's what's referred to as our label. So we're going to be branching or jumping to a particular label, not in our C code, although there's a direct one-to-one equivalence here, but in our assembly code. So there's a number of these different instructions. Supporting and implementing the first one is the hardest, and then the rest are just small little changes on top of it. This is definitely something that each ISA seems to do slightly differently, um, but conceptually they're all trying to accomplish the same thing. So MIPS does it via explicit instructions to check for different conditions. Um, when we get to that, we can talk about how other ISAs do it differently, and the textbook talks about that as well. But the simplest, or our first conditional test instruction, is referred to as branch equal or branch equality. Branch equal makes more sense to me, where it's going to then effectively implement that C pseudocode below here. We are checking, does the value in register 1, does it equal the value in register 2? If so, then we want our next instruction to be whichever one is encoded via that label in our assembly code. But there's an implicit else there that's not being listed here, right? The else is, if they're not equal, then what should we do? So branch equal, if register 1 and register 2 are the same, go to label. You can think of it as a literal go to statement, right? If register 1 and register 2 are not equal for this instruction, carry on. Just continue on. Just go back to our fetch, decode, execute cycle, where we just go to whatever the next instruction happens to be in memory. The architectural implications of this are kind of important, and once we get through a few examples here, we'll jump back into that, because knowing what this instruction is doing is one thing. So it's literally effectively implementing this C code with our branch equal instruction. What that means from an architectural perspective is something I don't think you would have seen in prior courses. So that's branch equal. There's also a branch not equal instruction, which you can imagine what that does. So if A is not equal to B, or if register 1 is not equal to register 2, then we do our go to. Then we branch to our instruction labeled by L1. Otherwise, continue on. Just continue on with whatever our next instruction should be. Those are our two most basic conditional branch instructions. When you look at the MIPS green sheet or the appendix at the end of your textbook, there's a lot of them. If we get a good feel for branch equal and branch not equal, we're in pretty good shape this semester. And then there's just the jump instruction, and that's unconditional again. There is no else case here. No matter what, if we've gotten to a jump instruction, our next instruction will be the one corresponding to that label in our code. So we can do a quick if then else example. If this is our C code, this is our so-called control and data flow graph corresponding to that C code. And this example is going to be relatively straightforward only because we're basically implementing branch equals in our C code. But if some variable I is equal to j, this is the next line of code we want to execute. Otherwise, else, we want this to be the next line of code that we're going to want to execute. So we can visualize that as a control flow graph here, where our if statements are these sort of diamond operators here, and that's our condition that we're checking, for which there's then a true side of the conditional and a false side of the conditional. Either I is equal to j, or it's not. If it is, this is what we want to do. Otherwise, this is what we want to do. Ultimately, for our if statements, we eventually get back to whatever's over here afterwards, whatever that next block of code is, whether we took the if true or the else side of the conditional operator, we get down to here, whatever is next here. In this case, we just label an exit for that block of code. In our MIPS assembly equivalent, yeah, we will definitely talk about this. In our MIPS assembly equivalent, we do have to create at least a label to make sure that we know what those next instructions we want to have are. In this case, you could call the labels whatever you want. There may be some limits in the assembler of the length of the labels and special characters and things like that, but otherwise it's just a label that's there for human readability of your assembly code, where we have that I equals j case corresponding to a branch equal instruction. There's more than one way we could have implemented this, but in this implementation, we want, if I is equal to j, we want to do in that true side that add of g and h and stored into f. Otherwise, in that else, in this case, we implement this as a fall through, we want to do a subtract instruction. So for f now being set as g minus h. Unlike this control flow graph where we're kind of visualizing somebody driving and either physically going here or physically going down this path here, right? Our instructions are still going to be laid out sequentially in memory, right? Our instructions are just data. They have addresses associated with them. They're stored as bytes in our main memory here. So we may have this conceptual branching happening, but in reality, both of those branches are going to be somewhere near each other in the code. That's why we have that unconditional, this jump here afterwards. So even if we fall into the true branch, f equals g minus h via that subtract instruction, we don't want to then inadvertently also execute the other side of the branch as well. It's one or the other we're wanting to do. Either way, then, we execute the one side of the branch. We then have to make sure we jump over the other side of the branch. There isn't actually any physical branching going on here. There's no concurrency of choices as it's kind of implicated by having these two things being side by side here. They're both there. Both branches are in the code. We need to make sure we're executing one side of the branch or the other side of the branch and not both. That's for equal and not equal. The way MIPS supports more complex conditional arithmetic operators, less than, greater than, less than, equal, and so forth, is to have an explicit set less than instruction. And there's nothing wrong with this approach. Other ISAs have specific condition flags and condition codes that it can check at any given time. MIPS explicitly forces you to use a register to store some comparison operator if you need to do something that's not just equal or not equal. So for this C code example, it's if f is less than g, then do our arc02. We don't have a branch less than, not as a native instruction in the MIPS ISA. So one way we can support that is by having an instruction that actually does a setting of 1 when a less than condition is met, and then just comparing the result to 0. So in this case, we would basically be using a temporary register T0, where T0 is going to be set to 1 if S0 is less than S1. So set on less than and set to 1. That's what set is meaning here. And then there's something of a double negative we have to kind of keep in our head here, where we want to actually do the branch when that value is equal to 1, right? And we don't have a value of 1 necessarily stored in some register to compare against, but we do have 0, right? The ISA specifies there's this 0 register, it is the 0th, it's the first entry in the register file, that always is hard-coded to a value of 0. That's very useful for these comparisons, but it does lead to something of a double negative, right? We set T0 to 1 when that less condition is true, and so that less than condition we can branch if it's true only when T0 is not equal to 0. So it's kind of a double negative there. And when you're working on these things and you're testing your own code, uh, you'll get it backwards, and that's okay. Then you'll test it, and then you'll just switch your branch equals to branch not equals, and then it'll work again, and that'll be perfectly fine. But that's what that is attempting to do here. This sets it to 1 if the less than is true, and then we can explicitly compare it to 0 to determine whether or not we should be taking that branch or not for that case. And so that's another design pattern we'll be seeing a lot of. So for our more complex comparisons, you will see this design pattern of a set less than instruction, followed by either a branch equal or a branch not equal, comparing that value to the 0 register. That'll be an extremely common design pattern. In that C code we were starting with at the beginning of the week, where we're checking if A is less than 8, well, MIPS does allow for a set less than immediate instruction that does exactly what it implies it's doing, that we are comparing a register value to a constant value, and it sets that value if that comparison actually turned out to be true. Sets a destination register if that comparison turns out to be true. And for better or worse, there's also an unsigned variant of those two instructions where we treat the values as being positive versus as being 2's complement, potentially negative values. So for our if A is less than 8, we would have a set less than instruction to compare to 8, and only if that value is set to be true should we continue on. Otherwise, we should get out of this block of code and we should take the else path. And that's what this example is doing from our original kind of hacky calculate 2 to the power b plus c code. The equivalent of this line is, do we want to take that if or not? That's then going to correspond to a set less than of 8, and then a branch to get to the else side of our code here. Questions before we jump a little bit into the uh, into the architectural implications of that. Question about whether we should be keeping track of our instructions. Yes. Well, I mean, it's fine. That'll seem silly in a couple weeks because you'll get very familiar and comfortable with these. There is many resources available for you. So there's the MIPS green sheet. It's literally that first green kind of tear off sheet in your physical textbook, or it's a separate little one-page PDF. If you have the online textbook, it's also posted on Canvas. That has every single instruction and all the information about it. That's a very useful one-page reference. It's in that register transfer level type of syntax, so it can be a little hard to parse if you're not really fluent in doing so. There's also an appendix at the end that discusses every single instruction and what they do. We're talking like 33 instructions, and you will know them all in the next few weeks here, and you'll become intimately familiar with them. Um, and the nice thing is, oftentimes there's many different ways to implement the same functionality. So it's okay if you can't really recall this particular instruction. There's usually another way to be able to do it. But that is something that we kind of expect you to be picking up this semester. So we're understanding assembly level programming. and the architectural implications of implementing an ISA. And yeah, take notes. That's fine. It's a good use of your notes. And I didn't answer the other question, but let's talk about that. So let's talk about what it means to implement control flow. You know, what is actually happening in our implementation of something like a branch equal or branch not equal instruction. Um, can everyone see that? Yeah, everyone can see the whiteboard here. Let's see if it's actually working. Of course, it's not. Um, there's a lot to talk about here, and we don't get to it all today. That's okay. We can continue on with this on Monday. So the question that was asked is, is the branch instruction actually doing the comparison as well as the branch? The answer is yes, but what that actually means really depends. So um, if you were studying ARM ISA in 288, instead there's a special register that is storing things like whether there was equal or zero or other conditions. In MIPS, that's not the case. It doesn't use a condition register. The branch instruction is actually doing the equality or inequality check. But before we even get to that, let's talk about what it would mean to do any type of control flow in our code, right? Because by default, as we have our assembly sequences, we have our add instruction and the actual details of what that instruction is doing, followed by a sub instruction. And then now perhaps we're going to have these condition sequence here where we're doing a set less than of some value, followed by a branch equal of 7 with, we'll just call it 0, to some label. So by default, if it's not a conditional instruction, right, we have this so-called sequential execution model. We referred to that as our fetch, decode, execute cycle. This was back on day one, and that was years ago, and I understand that. But the idea being that there's some logic in our processor that's determining what the next instruction is supposed to be, and it's fetching it from memory, right? Ultimately, all of these instructions themselves are just data in memory, right? This add instruction is some 32-bit value, and that's just our little block of memory. And we haven't talked about the details of what's actually in there. We saw a brief example of it in the first week, but somewhere there's some binary fields that let us know that that is an add, and other binary fields where the value of 1 for our destination is encoded. And that's the case for all of these instructions, right? We think of them as being this human readable thing, but they have a direct one-to-one connection to a 32-bit value stored in memory. And that's our stored program concept, right? Our von Neumann model of computing, where data is data, but instructions are also data. So we talked a little bit about, for load word and store word, how we have this main memory, and it's exactly the same for our instruction fetch cycle as well. It is not a separate concept. It is the same concept. See how that goes. There we go. Where we have some addresses in memory. I am always putting them at 1000 hex for some reason. There's no reason for that. Just some location that our things are being stored in memory. And in terms of where things are being put in memory, for our MIPS ISA, these are 32-bit values. All of our instructions are 32-bit values. That makes this logic so much simpler than if it were any other way. So what is actually being stored in this memory at, let's say, address 1000 would literally just be that add instruction. That first one that we had above. Not showing all the ones and zeros. It's not actually the word add, right? It's whatever the opcode is equivalent with our add instruction. And then the next location in memory would be the actual 32-bit encoding of our subtract instruction and so forth. So if you think of your instructions as being just a separate array of ints in our memory, that's completely valid, right? That's exactly what they are. They're stored in a different location. We have to be very careful with where they're stored, but they are just 32 bit. They're just ints, right? They're just words, instruction words stored in memory. This is just a physical memory, right? Ultimately, there's going to be two ports associated with it, right? There's going to be some sort of address port, just like for our load words, and then there's going to be ultimately some sort of data port, also 32 bits. So what makes this different from just the loads and stores that we're already doing is for loads and stores, we know our ALU, our adder, or whatever is going to be calculating pointers for us. That's what that instruction allows us to do. We either do it in one instruction or it takes a few instructions to calculate our pointer. Here we have to have some other mechanism to calculate effectively our instruction pointer. And it turns out that all ISAs have a special register that generally, although this does depend on the implementation, is not part of the main register file, but is a special purpose register specifically to address accessing things in memory. There are a lot of different names for that. Intel calls it the instruction address pointer, and I think that's a very appropriate name. Or IAP. Uh, Very appropriate way to describe what this thing is doing. Logically, if I were naming things, I would call it like the what instruction is next. No one likes my naming conventions though. It's going to be a special register that's keeping track of what instruction, which instruction, whatever, what instruction is next. That's our win pointer. Unfortunately, and for historic reasons that I can defend but still are kind of annoying, many such ISAs refer to that special register as the program counter. Because it is a counter and it is for the program. But in terms of logically what it's doing, either of these first two names is a more accurate depiction of what it is. But in terms of our implementation, it's not in the register file directly, but it's going to be a separate, and here's our little diagram element for our register. It's a little slanted, and that's going to be our PC, our instruction address pointer. It's literally a 32-bit value that we're going to physically connect to our address line for our instruction memory here. It is determining what instruction is next, our pointer into our instruction memory, and that is the value. If we wanted to label this, if this was VHDL, we'd probably want to label this and call this PC value or something like this for the name of the signal that's physically connecting. And by default, life is pretty easy, right? By default, we execute this instruction, and the next one that we fetch is that next sequential instruction. So there is some math implied by just being able to support that we have a current PC value of 1000 hex, and we want to then load the next instruction after the current instruction is done. What do we have to do to that PC value then by default? What other logic element or functional unit would we need here? Left shift would be like a multiplier. That's a good thought. In this case, though, and there may need to be some shifting eventually. In this case, if we knew that our current PC value is 1000 and it's not a branch instruction, it's just a regular give me the next instruction operation, we need to be adding a certain value to that, a certain constant to it. We need to be basically counting our way through memory. Hence the term program counter, which I still don't like the term. That's our little plus operator there. And in fact, though, because it's our byte addressable memory model in MIPS, we would be adding, 4 to it, right? Not explicitly with an add IU instruction. There would be sort of a circular issue here, right? We'd be doing the equivalent of an add IU operation, but it's probably going to need to be, from a microarchitectural implementation perspective, a completely separate adder than the one that we have for our add I instruction. Because it's possible that both things are happening simultaneously, and that would be one way of implementing this, in which we have an add instruction, which needs to make use of an adder, but for every instruction, we're having to figure out what the next program counter is going to be. And so either we take multiple cycles and do it extremely slowly, which is a valid implementation philosophy, or we have a separate adder specifically to keep track of what the next program counter should be by default. And I don't think we can get to the rest of the implementation details of how we would then support, because this would get us through our add, then our subtract, then our set less than. But the way it works in practice is coming in from our implementation somewhere is going to be our branch target address, it's referred to. It's however that label that we have in the assembly instruction is going to get encoded as a 32-bit value. The assembler has some ability to determine that for us. We can actually just count the number of instructions we're branching ahead or behind and get either a positive or negative value for that for an offset. And then ultimately, we have two potential things that could be our next program counter, either just the next sequential instruction or what our branch target is based on if it's a branch instruction. Two possible things that we may want. Only one of them we actually want at any given time. That would then correspond to our mux. Sort of an if statement in our implementation. We would call this one like next PC or something, where we would then have to determine, what is the condition at runtime for which we should take a PC plus 4 value, or whether we should be taking the actual branch target value, which I'm not showing how that gets calculated, but we would have to determine that. That's what that mux would be determining. We have about a minute remaining today. Any thoughts as to what could be feeding in this select line for that mux? Again, that mux is an if statement, right? Give me one of those two values. We'll label the input so it's clear which one is which. By default, give me PC plus 4. Only if that select line is 1, give me the branch target to actually go to label. What things can we check for that to be the case? That's a good start. So the jump, go to opcode, jump instruction. Yes, absolutely. So we're dealing with branches right now and not the unconditional jumps, I guess. But that's absolutely the case. There would have to be some signal in your design, whether we're checking the opcode here or we separately use the opcode to generate this signal. There's a lot of complexity that's still hidden, but you would want to have some signal in your design that's supposed to say is branch. Is the instruction I'm currently executing a branch instruction? Calling it branch equal or branch not equal would also be a valid name for that signal, that control signal. Is it a branch instruction we're wanting to execute? That's actually not sufficient for branch equal or branch not equal. That's necessary but not sufficient. As opposed to stressing out about it today, we would need to know that that signal is one, but we would also need to know that not only was the instruction a branch instruction, but is the condition true? Was it actually equal to the things we wanted to be equal, or was it not equal if we wanted it to not be equal? That signal we still have to calculate in our design somewhere else, but ultimately we would label that output wire from that piece of logic something like branch should be taken or branch taken. Both of those conditions would have to be true, right? In order for us to want to take this second path versus our default path, both those things would have to be true. It would be, yes, there is a branch instruction that we're currently executing, and how we calculate that is branch signal is something we will still talk about. I've mentioned control code spreadsheets, and that would be part of it. And then separately, something that's doing some math to tell us, yes, that branch should be taken, or no, in fact, even though it was a branch, the condition wasn't true. We should not be taking that branch. So, in the interest of time, let's leave things here for today. You do have your homework 2 out today, which is getting started with MIPS programming and understanding more of the MIPS ISA. It's straightforward, but please don't start at 2 in the morning the night before. I know it happens. Um, Give yourself some time to pace it out. We're in that steady state of the semester where you have current lab. It'll take a gander at the pre-lab for the next one, and then you have your homework each week. So you really do have to pace your time, and space things out accordingly to be successful in this class. Otherwise, as always, let me know if you have any questions, and I look forward to seeing everyone on Monday. Thanks.